Have you ever really stopped to think about what makes our crazy, fast digital world actually work? We're streaming movies in HD, sending huge files, talking to people halfway across the globe. It all seems so effortless.
We definitely take it for granted, but behind every click, every bit of data, there's this incredibly complex, almost invisible technology making it happen.
Exactly. It's like this hidden backbone, powering everything from, your internet at home to the traffic lights you see every day.
And often without us even realizing the sheer scale of the infrastructure involved.
Right. And that hidden complexity. That's what we're diving into today. Welcome back to The Deep Dive.
The show where we take these big, complicated subjects and break them down.
We cut through the jargon, pull out the essential bits, the stuff you really need to know.
Yeah.
We want to save you time, but still leave you feeling genuinely informed.
And today we're focusing on fiber optics hardware and connections. The tiny, super precise bits and pieces that make all this digital communication possible.
And a quick note on our source here, this deep dive. It leans heavily on a really comprehensive presentation. It was originally put together by AtkinsRealis, specifically for the Florida Department of Transportation.
That's right. So what you're hearing gives you a real inside look at the kind of material FDOT themselves use to understand and, implement these critical systems. It's a pretty granular view.
Yeah, I'm actually pretty excited about this one. It's not often you get to peek behind the curtain at something so fundamental, yet so surprisingly complex. Okay, let's get into it. So just a quick refresher from maybe a previous session, or for anyone just joining us. Data travels as zeros and ones, right? Little digital bits.
Yep, the fundamental language.
And fiber optics. It uses incredibly fast pulses of light to zip that information along. The cables themselves are pretty sophisticated. You've got the core, the cladding around it, buffer tubes protecting groups of fibers, a central strength member, and then the outer jacket holding it all together.
It's a layered defense system, really, for those delicate glass strands. And getting the light out of those strands and into the network involves two main ways connecting them: splices and terminations.
Splices and terminations. Got it.
And remember, each individual fiber we're talking about is about the diameter of a coarse human hair, maybe even finer.
Wow.
So the precision needed is just, well, it's astronomical.
That precision, that human hair scale.
Yeah.
It actually brings up something really interesting about how the Florida Department of Transportation, FDOT, pays contractors for this work. It's kind of unique.
Oh, yeah. How so?
Well, unlike a lot of other states, or even just general construction where you might pay for, say, the pipe and the labor to install it separately.
Right, material and action.
Exactly.
Yeah.
FDOT often bundles fiber optic work, but with a real emphasis on the action over just the material. Think conduits, it's usually furnish and install. You pay for the pipe and putting it in the ground.
Makes sense.
But for fiber connections, especially splices, they often focus payment on the action only. They pay for the act of making that perfect splice, not necessarily every little bit of material involved.
Huh. That really underlines how specialized they view this work. It's not just about providing parts, it's about the high-skill process itself.
Precisely. The equipment, the skill.
Yeah.
It shifts the focus onto successfully making that connection.
Okay, so let's dig into those connections then. Starting with splices, what exactly is fusion splicing? It sounds intense.
It does.
It is, in a way. Fusion splicing is how you permanently join two individual fibers together, physically fusing them. The whole point is to create one continuous path for light. No gaps, no interruptions.
So not just plugging things together.
No, definitely not. We're talking about melting glass end-to-end at a microscopic level. It uses intense heat, usually from an electrical arc or maybe a laser, inside a special machine called a fusion splicer. It melts the ends just enough to fuse them into a practically seamless bond.
And this is where that precision we mentioned becomes absolutely critical. We're dealing with light here.
Exactly. Light doesn't behave like electricity in a wire.
Right. Like, imagine shooting a laser down a fiber that just stops. The light would just bounce out, right?
Yeah.
Or, if the connection isn't perfectly aligned after splicing even slightly off-center, you get signal loss, attenuation.
Think of it like a leaky pipe. Some water gets through, maybe most of it, but some leaks out. With zeros and ones, that lost light means lost data packets.
And the scary part, you might not even know what's happening. The connection might seem okay, things might look like they're working.
But you're losing information silently in the background. That really drives home why that surgical precision is so vital.
Absolutely. A bad splice can have hidden consequences for the network's reliability.
Yeah.
And the process itself. It's incredibly meticulous. It has to be perfect.
Walk us through it. How does it work?
Okay, well first, you slide a little protective heat shrink sleeve onto one of the fibers. You'll need that later.
Then, step 2, you carefully strip back the protective coating, the buffer, and acrylate to expose the bare glass fiber, just the core and cladding. And then you have to clean it meticulously. Alcohol wipes, usually.
Like prepping for surgery.
Kind of, yeah. Then comes the cleave. Step 3, this is crucial. You use a special tool, a cleaver, to cut the fiber end perfectly flat, exactly 90 degrees, any angle, any tiny chip.
And the light scatters.
Big time. Reflections, loss. It's bad news. So perfect cleave. Then, step 4, you place that prepared fiber end into the guides on the fusion splicer and clamp it gently in place.
Okay.
Then you repeat steps 2 through 4 for the other fiber you're joining it to. Get both ends prepped and loaded.
Got it. Both sides ready.
Step 6, hit the button. The splicer does its magic, aligns the fibers automatically using tiny motors, often checks the alignment with cameras, and then fires that electrical arc to fuse them. No human holding a lighter, thankfully.
Right. Good to know.
Then, finally, step 7, you slide that heat shrink sleeve you put on earlier over the bare splice point, and you place it in a little heater oven built into the splicer. That shrinks the tube tightly around the splice, protecting the fragile fusion point.
Wow. That's a lot more involved than just plugging in a cable. It sounds like a real expert craft.
Oh, it absolutely is. Highly specialized. I mean, just the fusion splicer machine itself can cost anywhere from, say, $15,000 up to $40,000.
Serious investment.
Definitely. And the technicians who are good at it, they're artists. There are stories like, I heard about a guy named Phil from ACS who could supposedly knock out 12 perfect spices in just 12 minutes. That's incredible speed and accuracy.
That's amazing. And it needs that super clean environment too, right? You mentioned the human hair thickness.
Critically important. Usually they work inside dedicated splicing vans or trailers, clean, controlled environments. Because think about it, a single speck of dust between those two perfectly cleaved fiber ends, it can completely ruin the splice, cause massive signal loss.
And they're sometimes doing this out in the field. Maybe temporary fixes.
Yeah, sometimes conditions aren't ideal. You might see techs working off folding tables, doing their best to keep things clean, but it's tough. The Fiber Optic Institution of America actually estimates it takes about 55 minutes, typically, to prep and splice a 12-count fiber cable properly.
55 minutes for 12 tiny connections.
Roughly, yeah. Maybe 25 minutes for prep, 30 for the actual splicing and coiling the fibers neatly into the tray. It just shows the time and skill involved.
Okay, so that's splicing the permanent fusion. What about the other type? Terminations.
Right, terminations, or sometimes called connectorization.
Catchy.
Huh. Well, this is how you actually connect that fiber strand to a piece of equipment. Instead of joining fiber to fiber, you're putting a connector on the end of the fiber.
So like putting the plug on the end of an electrical cord.
That's a decent analogy, yeah. It provides a standardized physical interface so you can plug that fiber into a switch, a router, or maybe another patch panel.
Makes sense. What are the main parts of one of these fiber optic connectors? If we could sort of explode one out.
Sure. You've basically got 3 main parts. There's the housing, which is the main body you see and hold. It gives the connector its shape, like SC, LC, and handles the locking mechanism.
Okay, the outside bit.
Then inside, you have the ferrule. This is probably the most critical part. It's a tiny, precise cylinder, often ceramic, with a microscopic hole down the center. It holds the bare fiber perfectly aligned.
Ah, so that's where the alignment happens.
Exactly. And finally, there's usually a flexible boot at the back. That just provides strain relief, preventing the fiber from bending too sharply right where it enters the rigid connector body. Protects it from breaking.
Got it. Housing, ferrule, boot. Now, are there tons of different connector types?
Oh, hundreds exist globally.
Yeah.
But for standardization, FDOT keeps it simple. Their specs only allow 4 main types: LC, ST, FC, and SE.
Okay, 4 to remember. LC, ST, SC, SC, SC. Are there, like, easy ways to tell them apart?
There are some handy mnemonics.
Oh, good. Lay 'em on us.
All right. LC is the little connector. It's small, often used where space is tight, high-density panels. It usually has a little clip, sort of a snap-in feel.
LC little connector. Okay.
ST thinks stick and twist. It's got a round bayonet-style connector. You push it in and twist it to lock.
ST stick and twist. Nice.
FC, some say ferrule connector or even screw F. It's threaded. You screw it on securely. Takes a couple of turns.
FC screw connector. Got it.
And SC, maybe standard connector or stout connector. It's a bit chunkier, squarish body,
Right.
and it's also a snap-in or push-pull type.
SC stout connector. Okay, LC, ST, FC, SC. That helps.
Good. And you'll also see duplex and simplex. Duplex just means two fibers, usually transmit and receive, often clipped together in one housing. Simplex is just a single fiber connector.
Right, two-way versus one-way. And what about colors? Do they mean anything?
They do. The color of the connector body, or sometimes the boot, often indicates the fiber type and polish. Like beige usually means multi-mode fiber. Blue often means single mode with a standard UPC polish. And green typically indicates single mode with an APC or angled physical contact polish, which reduces reflections.
Ah, so a quick visual check can tell you a lot. Useful. How do you actually install one of these connectors? Is it like splicing?
Similar steps in preparation, but the end goal is different. First, you slide the strain relief boot onto the fiber. Then, again, you strip the coatings, expose the bare fiber, clean it thoroughly.
Okay.
Then you cleave it again. That perfect 90-degree cut is essential for getting light into the connector properly.
Right. Got to have that flat surface.
Then you typically prepare the connector itself, maybe inject a tiny bit of epoxy if it's an epoxy-style connector. You carefully insert the cleaved fiber into the back of the ferrule until it's seated. Secure it, either the epoxy cures, or you might crimp part of the connector body onto the fiber buffer for mechanical grip.
So chemical or physical bonding?
Pretty much. Finally, you slide the boot up, assemble the main housing components, and sometimes you need to polish the very tip of the ferrule and fiber to get a perfect optical surface, though many modern connectors are no polish.
Seems almost as intricate as splicing in its own way.
It definitely requires care and the right tools.
So we talked about signal loss at splices. I assume you get loss at terminations too.
Absolutely. Every connection point, every splice, every termination introduces some amount of signal loss or attenuation. It's unavoidable physics. Minimizing these connection points and ensuring their high quality is key in network design.
Right, because those losses add up over the length of the connection.
Exactly. Too much loss, and the signal becomes too weak for the receiver to read correctly.
Okay, so we've got these delicate connection points, splices fused together, terminations ready to plug in. They obviously need protection and organization. Let's talk about the hardware that does that.
Good transition. And when we say hardware here, we mean the passive stuff. No power, no active communication role. It's all about housing, protecting, organizing the fibers and connections. Think of it as the support structure.
Got it. Not the active devices like switches.
So looking at that diagram from the FDOT material, you see cable coming in, maybe branching off.
Yeah.
What are the key pieces of this hardware ecosystem? Let's start with those things everyone calls pills. Fiber optic splice enclosures.
Right, the pills, or sometimes drums. Their job is simple. Provide a tough, environmentally sealed container for splices, keep water, dust, bugs, everything out.
Protect those delicate fusion points.
Exactly. They have ports for cables to enter and exit, structures inside to hold splice trays securely, and usually a removable cover or housing so technicians can get access.
And you mentioned pressurizing them.
Yeah, best practice is often to pressurize them slightly with dry air or nitrogen. That positive pressure helps ensure nothing gets in, even if a seal isn't perfect. You sometimes see them floating in floated manholes still working because of that pressure. But it doesn't always happen.
No. It adds complexity and cost, so it sometimes gets skipped in the field, unfortunately.
And they're not always pill-shaped, right? I've seen square ones.
True. The name sticks, but the shape can vary. Inside these enclosures, you find the splice trays, sometimes called cassettes.
Okay, what's their role?
They're basically thin, hinged organizers, usually plastic. They hold the actual fusion splices and allow you to carefully coil the tiny bit of excess fiber slack for each splice. Keeps everything neat, protected, and manageable within the enclosure, or maybe a patch panel.
How many splices per tray?
Standard is often 12, matching a 12-fiber buffer tube. But you can get 24 splice trays, too. A good rule of thumb in design is 1 tray per buffer tube you're splicing from a single cable.
Makes sense for organization. Okay, next up, patch panels, also called distribution panels. These seem important.
Very. They're the central hub for managing fiber connections within a building, a cabinet, or an equipment rack. Again, they're passive, just a housing unit. They provide a place to terminate fibers and then cross-connect them, usually via jumpers, to the active equipment.
So the main interface point.
Pretty much. They come in different sizes, rack mount or wall mount, holding various numbers of connections, typically multiples of 6 or 12.
And you mentioned an FDOT debate here.
Okay.
About what a patch panel actually includes.
Yeah, it's a bit of an internal point of discussion, apparently. Does patch panel refer just to the metal or plastic housing itself? Or does it imply the whole assembly housing, connector panels inside, maybe even pigtails and splice trays?
I can see how that ambiguity could cause issues, especially with payment. We'll come back to that. So related to patch panels are connector panels, adapter panels.
Right. These are the small plates, often removable, that snap into the front of the patch panel housing. They're the bits that actually have the holes, the adapters that the fiber connectors like SC or LC plug into.
Ah, so the patch panel is the box, the connector panel is the faceplate with the ports?
You got it. They come preloaded with specific adapter types like a 6-port LC duplex panel or a 12-port SC simplex panel.
Okay. Now what about pigtails? Pre-terminated connector assemblies.
Pigtails are super useful. Imagine a short piece of fiber optic cable. On one end, it has a factory-installed connector, like an SC or LC. The other end is just bare fiber.
Okay, connector on one end, bare on the other.
Exactly. You buy them usually in bundles of 6 or 12. The connector end plugs into the back of a connector panel inside your patch panel. The bare fiber end then gets routed to a splice tray, where it's fusion spliced to the incoming field cable.
Ah, so it lets you have a nice, clean, factory-made connection at the panel, but still allows for field splicing.
Precisely. It avoids having to do the tricky connector termination process out in the field environment.
Clever. Now, how are jumpers different? They sound similar.
Similar, but a key difference. Jumpers have factory-installed connectors on both ends.
Oh, okay.
Yeah.
Connector.
Right. Think of them as fiber optic patch cords. You use them for making connections between hardware or from hardware to active devices, like connecting one port on a patch panel to another or connecting a patch panel port to a port on a network switch.
So they jump between connection points.
Exactly. And they're really versatile. You can get them with the same connector on both ends, LCLC, SCSC, or different connectors like SCLC if you need to connect different types of equipment.
And they have that color coding too, right?
Yep. Vital cue. Orange typically means multi-mode fiber. Yellow always means single-mode fiber. If you open a cabinet, that color instantly tells you what kind of fiber you're looking at in that jumper.
Good visual check. And payment-wise.
Jumpers are usually considered incidental, meaning they're necessary for the system to work, but they aren't typically paid for as a separate line item in a contract. Their cost is expected to be included in the overall cost of installing the connected hardware or devices.
Got it. One last hardware bit. Buffer tube fan-out kits. What are those?
These are mainly used when you're doing direct field terminations onto fibers from a loose tube cable. Those individual 250-micron fibers are really flimsy. A fan-out kit provides little protective tubes, often color-coded, that you slide over each individual fiber.
Ah, like giving each tiny fiber its own mini jacket.
Exactly. It builds them up to maybe 900 microns, making them much easier and safer to handle and terminate directly with a connector rather than splicing to a pigtail. You wouldn't typically need one if you're using pigtails because the pigtail fibers are already protected.
Okay, that makes sense. So if we imagine putting all this together, you have the main cable coming into an enclosure, maybe spliced to a drop cable. That drop cable goes to a patch panel housing. Inside, you might have spliced trays connected to pigtails. The pigtails plug into the back of connector panels. And then jumpers connect from the front of the connector panels to your network switch.
That's a very common setup, yes. And crucially, all the connectors have to match at each interface point, the pigtail connector type, the adapter in the connector panel, and the jumper connector type. You can't plug an SC into an LC port.
Right, got to match shapes. Okay, this brings us back to that FDOT patch panel distinction in the payment puzzle.
Yeah.
This sounds potentially messy.
It can be. This is where the design choice really impacts how the contractor gets paid and potentially the overall cost. FDOT basically has two distinct ways of specifying and paying for patch panels.
Lay them out for us. Type 1.
Type 1 is the pre-terminated patch panel. The idea here is that the panel arrives from the factory with the connector panels, the pigtails, and even the splice trays already installed.
Yeah.
And it includes a stub-out cable, that drop cable we mentioned already attached, supposedly cut to the exact length needed for that specific installation site.
Wait, exact lengths. How exact?
That's the tricky part. The payment for this single line item pre-terminated patch panel is meant to cover the panel, and that entire length of stub-out cable, whether it's 50 feet or, theoretically, 5,000 feet.
Whoa. So the contractor bids one price for that item, but the amount of cable included could vary wildly. That seems risky for the contractor.
It can be.
Doesn't that just invite really high unit prices to cover the worst-case scenario? Or contractors getting caught out if the designer specified 100 feet, but they actually needed 500? And do manufacturers even ship panels with, like, 3,872 feet of exact length stub cable attached? Or does the contractor often end up having to splice it anyway?
These are all valid points and potential pitfalls of that payment method. It bundles a highly variable material cost, the cable, into a single item. Plus, this approach inherently involves both a factory termination and a field splice to connect that stub out to the main backbone cable, potentially adding more signal loss points.
Okay, so what's the alternative? Type 2.
Type 2 is the field-terminated patch panel. Here, the payment for the patch panel item basically covers the housing and maybe the empty connector panels.
Just the box and faceplates.
Essentially, yes. Then, crucially, you have separate pay items for installing the connectors, the field terminations, for the buffer fan-out kit if needed, and for the drop cable itself, paid per foot.
That sounds much more transparent. You pay for the box, you pay for the termination work, you pay for the actual cable lengths used.
Exactly. It breaks down the costs based on the actual work performed and materials consumed. Personally, I tend to recommend specifying field-terminated panels.
Why is that?
Well, for the reasons you mentioned. It ensures the contractor is fairly compensated for the specific tasks and cable length. It avoids those potentially hidden or inflated costs bundled into the pre-terminated item. It offers more flexibility in the field if cable lengths aren't perfectly known beforehand. It just seems like a cleaner, more equitable approach most of the time.
It really highlights a disconnect, though, doesn't it, between maybe some general guidance in FDOT's manuals and the specific way the payment items are structured?
It can seem that way. You might see guidance suggesting either pre-terminated or field-terminated connections are acceptable.
Right, that or gives wiggle room.
But then the detailed specifications section 633 lists separate pay items for almost everything. The splices, the terminations, the enclosures, the trays, the pigtails, the fan-out kits, 2 kinds of patch panels, the connector panels. It's incredibly granular.
So the payment structure allows for the field-terminated approach, even if the general guidance is ambiguous.
Precisely. And navigating that complexity is key for both designers and contractors. But, stepping back a bit, from the network owner's perspective, at the end of the day, the primary goal is a functional result. Does the connection work? Does the data get through reliably?
Does the light stay on, so to speak?
Exactly. If you test that connection with an OTDR that's an optical time domain reflectometer, a key testing tool, and it meets the loss budget requirements and the network devices can communicate, then the specific method used to achieve that connection, whether it was pigtails or direct termination, might become somewhat secondary. The system performs as needed.
That's a fair point. Functionality trumps method, ultimately. Though the payment method clearly matters a lot to the process. And just a final note for designers, it's still really important to check with the local agency or client about their specific preferences for connector types, like if they're standardizing on LC for all new installs.
Absolutely. Local standards often overlay the broader specs.
Okay, wow. We've covered a lot of ground here.
Yeah.
From the incredibly delicate art of fusion splicing and connector termination.
To the whole ecosystem of hardware enclosures, trays, panels, pigtails, jumpers that organizes and protects it all.
And finally, landing on these surprisingly complex, even contradictory ways these systems get specified and paid for, especially looking through that FDOT lens.
It really is a journey from the microscopic to the contractual. But I think the key takeaway, maybe the provocative thought to leave folks with, builds on that functional result idea. We get bogged down in the technical details, the specs, the payment items, and those are crucial for building these networks properly. But the real magic is how all this intricate, precise work with hair-thin glass translates into the seamless communication we rely on every single second.
We just don't see the complexity behind the screen.
Exactly. We stream, we connect, we work, often completely oblivious to the thousands of perfect splices, clean terminations, and carefully organized fibers making it possible. It's a testament to the engineering and the skill involved, but also a reminder of how critical and maybe how fragile this infrastructure really is. Maintaining and expanding it, that's a huge ongoing challenge.
That's a great point. So much hidden complexity enabling our simple clicks. And this is really just scratching the surface. We'll definitely be diving deeper into fiber optics in future sessions, looking at design principles, testing methodologies, maybe even some more hands-on aspects.
Lots more to explore.
Absolutely. Well, that brings us to the end of this particular exploration. Remember, this deep dive drew heavily from insights originally developed by AtkinsRealis for the Florida Department of Transportation.
Giving us that valuable real-world perspective.
Indeed. Thanks for joining us on the deep dive. We hope this shed some light on the hidden world of fiber optics. Keep exploring, keep questioning, and we'll talk to you next time.